components, just know what they're used for, when to use them. Like if probably we'd be given like a hypothetical scenario and like
Yeah,
when
or
to-
just ask what was the purpose of
Z-buffer.
this in this particular, yeah. What was the purpose of SDS in the beta-galactosidase experiment?
Oh no, I was hoping you wouldn't ask me that one because that's one I know. So I was
No.
hoping it would be on there, and now I assume it's not
What's
going to
the
be on there.
purpose of
Yeah.
SDS in
That's true.
a page gel? You have two different answers.
Hmm.
in a page versus
In the beta-galactosidase experiment that we did.
really there's two.
Yeah, so
That was actually one of the questions. That's question number 60.
if you remember in the
That's the one I
beta-galactosidase
marked. Okay,
beta-galactosidase experiment, we used chloroform and SDS to dissolve the membrane
Oh.
and so that we could release the enzyme and actually measure it. Right. So it's a detergent.
Yeah.
In a polyacrylamide gel, we're using it to actually denature proteins and give them a negative charge. Right.
Right.
So
So then
They're
they're
both
all,
given a negative charge.
yeah, and they're all monomers. They're broken apart.
Yeah.
yeah. So in one case, it was being used as a detergent to dissolve a membrane, and the other it was being used as a detergent to denature a
Oh,
protein
protein.
and give it a negative charge.
Oh, so one's used for the
For
membrane and one's
electrophoresis.
for protein. Okay, and the protein one was the one I was more familiar with.
Right.
Okay.
And that's commonly the application of SDS, but because it's a detergent, we can use it to dissolve a membrane.
And BME reduced the dual sulfide bonds. What was BME?
So beta mercaptoethanol,
Yes.
and it's dithiothietol
Yes,
is a cousin.
the
They're
substitute.
substitutable. So that, in the beta-galactosidase experiment, was serving as an antioxidant
Right.
to preserve the beta-galactosidase.
Yep.
In an SDS page gel, it's reducing disulfide bonds.
Yeah.
Right. So again, the same reagent being used for two different, they're related purposes, but they're different. So I would have to be careful if I just said,
Yeah.
what did you use dithiothietol for? That wouldn't be a good question.
Right.
But if I'm specific about
Which
the
labs?
context,
Mhm.
then that's a better question.
I see. There were some questions that you had asked in the lab handout that I didn't have answers to.
Okay.
And I don't know why. But did the L-DOPA spontaneously convert to dopachrome was one that I
Yeah,
didn't have an
so
answer to.
so you just put the L-dope in the buffer in the cuvette, and you didn't add the enzyme. Yeah, and it stayed at an absorbance of 0 for 2 minutes.
Hmm.
Right, so it didn't spontaneously
Understand
convert.
the question now, okay,
Yeah.
I see.
And so, and the rationale was it has a high activation energy requirement.
Right.
So now let's throw in an enzyme and see if we can actually start seeing that product.
Now I think I know why I didn't write the answer down, because it was so obvious at the moment. I was like, well, of course it didn't.
Well, of course it didn't. There's no absorbance change.
There were two more.
Mhm.
Did the tyrosinase accelerate or catalyze the formation of dopachrome?
Would that be the enzyme then?
Tyrosinase is the enzyme.
Yeah.
So when you threw it in there, did you start to see?
Yes.
Yes, absolutely, right? Yeah, it did, it worked. You know? And was the dopachrome production linear for 7 minutes?
Yes. Other than our first sample was off a little bit because of pipetting error probably.
Well, but for 7 minutes.
So what we did 14 measurements in 30-second increments,
Mhm.
and the line that we plotted was, it was a straight line.
I feel like ours went a little off. We started
Most people saw something like that. It lost linearity.
Oh,
over time.
Okay.
Why would it do that?
because it's starting to reach saturation, so it's starting to become saturated or equilibrium.
Equilibrium.
Which is it.
Yeah.
Either one.
We're not adding more substrate, right? We're just
Yeah.
letting it go a longer period of time. So that's allowing the reverse reaction to occur.
So, I'm confusing my graphs is why I was thinking of a different graph
Yeah.
for the linear line.
Right.
Andy?
Yeah, so if we just let time go by, right?
Yeah.
We're just measuring the amount of product, right?
Yeah.
Okay. This is the forward rate. This is the forward rate. That's what we want to be measuring.
Mhm.
The longer we let it go, the more reverse reaction is occurring,
Yeah.
right? So that's our justification for why we need to do really short measurements.
Right.
So we get
Yeah.
initial velocities
Yeah.
that aren't complicated by
The
the
reverse
reverse
reaction.
reaction occurring. I just wanted you to see that, to convince yourselves that, geez, the longer reaction occurs, the forward rate seems to slow down, right?
Mhm.
And it's not that, it's that the reverse rate is speeding up. Complicating your kinetic analysis. So after we did that 7-minute measurement, every single measurement we did after that was only 30 seconds
Yeah.
in an effort to try and capture an initial velocity
Okay.
forward rate.
That makes sense.
You might need to grab a chair.
I'll have to leave at 4, so someone can snag this one.
I think he has to leave at 4 too.
No, I'm good until closer to 5. So.
Meet again? Yeah, I'm gonna see.
Disadvantages that I had listed for the gas chromatography was that it destroys the sample,
Mhm.
and that you can't use something that's too volatile, otherwise it won't remain the same as it's vaporized. Is that, am I saying that
well,
right?
yeah, so I would say there's 3 disadvantages. One is it consumes the sample,
Mhm.
okay? The second one is the sample has to be volatile. You have to be able to convert it to a gas.
Oh, so it's not that it can't be too
Right.
volatile, it has to be volatile.
But there are some samples that are labile at elevated temperatures. In other words, elevated temperature destroys them.
Oh,
So you would want to be careful of that as well.
I see.
Yeah.
Labile.
It's the word. We should have word of the day.
Oh, I feel like there was one question.
You said you had another question. Has it come up?
It's kind of a small one, and it's probably obvious. It was about in discontinuous page.
Uh-huh.
So where you start
Mhm.
is neutral pH, or is that the charged pH?
Yeah, so at the stacking gel,
Mhm.
right? The pH is such that the carrier ion, which is glycine, is
Yes.
close to being zwitterionic,
Okay.
so it doesn't conduct very well.
Okay.
So the proteins pile up behind it, they stack.
Okay. So.
And then the pH changes so that the glycine has a net negative charge.
Mhm.
So it's no longer constrained, and the proteins can start to separate from one another.
Okay.
And that's in the resolving gel.
Makes sense. So it's all glycine, just different.
It's
pHs.
just changing the pH so that the glycine is not a good conductor,
Mhm.
and then it becomes a good conductor. Yeah.
Thank you.
Wasn't it made like more
Makes sense.
basic in the
From
results?
about 6.8 to 8.8, yeah.
Okay.
Mhm.
So I was reading about like the void volume. It said the volume outside or in the beads.
So void volume is outside the beads.
Okay.
Yeah. Bed
That's what I thought.
volume is both outside and inside.
Okay. And then we're looking for the elution volume.
So the elution volume is whatever the volume that your sample comes out in.
could be equal to the void volume, it could be equal to the bed volume, or it could be between the bed volume and the void volume.
It- If y'all are okay with it, I can share he went through this in detail on these, on the differences, and I can share the video with you.
But that makes sense, right?
Yeah.
Have you guys gone over most of the calculation stuff?
We did some stuff, but I don't have a problem with.
Well, I can just rewatch this video. That's just kind of what scares me the most.
Fear of the calculation.
Oh, for sure.
Well, I just can't, I'm too disorganized, I can't follow my notes.
I think I made all those questions are.
Okay, so knowing when I need to do what type of calculation,
Mm-hmm.
like the y equals mx plus b, that's easy. I'm solving for x,
Mhm.
right?
It depends on what you're trying to calculate.
Or I might be doing Beer's law.
Not with line for, or an equation for a straight line.
Okay.
Right.
The only time you'd use Beer's law is if you have some sort of an absorbance, right?
Right.
Like 0.932 absorbance at 420, let's say. And you need to convert that into a concentration.
Okay.
Like
That makes sense.
millimolar or something
Yeah.
like that. That's, Beer's law converts measured absorbance into concentration. Right.
Thank you.
Yeah, we're converting that into that.
My concentration could be at the solute then.
Yeah, of whatever it is that you measured, whatever it was absorbing in the first place.
Yeah.
And of course, you have to know its molar extinction coefficient.
Right, that'll be given.
And so the unit you're going to get is moles per liter, because that's a molar extinction coefficient.
Okay.
And then you may be required to convert it into micromoles per liter, or just plain old micromoles, in which case you'd have to multiply by the volume that's present in order to get it to just be moles.
The one thing that we haven't gone over specifically is this here, where each of these are turned into columns. And I can't remember how we would use what we would be trying to do when we would use that.
Well, so you would be generating a graph, the concentration of L-DOPA, which is your substrate, versus the corresponding initial velocity.
Okay.
Right? So you have to, in your experiment, you pipetted a volume of L-DOPA. So I had to give you the concentration of the L-DOPA for you to figure out what its concentration was after you put it into the cuvette, right?
Right.
Right, and that's what this column is giving us. It's giving us the concentration of the substrate.
Okay.
Right? Here, you're taking your measured change in absorbance and using Beer's law to convert it into an amount of product.
Right.
Right? So you first convert it into moles per liter, and then you convert that to micromoles per liter, and then you multiply that by the number of liters, and you have micromoles. So once you have this column and you have this column, you can generate a graph.
Okay.
Right? And I wouldn't have you do 18 calculations of a whole bunch of different concentrations and a whole bunch of different velocities, right? If I did anything, it would be to have you calculate one of each, right? But what I'm most interested, since this is a kinetics lab, I'm most interested in you being able to calculate the kinetic parameters, the Vmax, the Km, the Kcat.
Good.
Right. So.
I gotta run.
I have one more small
Mhm.
one. It was just this one, the small sample volume. Was that the only thing I remember is that if we put it on top, it can cause like a dip in your gel and make it uneven, or is that a separate?
It's a little bit different,
Okay.
right? So, so let's say this is our column here.
Thank you, thank you.
No, we didn't yet.
Right, this is our column, and then here's another column. Not intentionally sideways, right?
No.
So let's say this is a gel filtration column,
You could ask him that. I haven't
and then
said that.
this is an ion exchange. Right? Okay, so let's start with ion exchange. What's the principle by which ion exchange separates molecules from one another?
Charge.
Charge, right? The beads are charged. Anything that's an opposite charge will stick. Anything that's the same charge will pass through. So the volume doesn't matter, right? You could put on a milliliter, 2 milliliters, 10 milliliters. It's gonna run through. Whatever's going to stick will stick. Whatever doesn't stick won't stick.
Okay.
As long as you don't saturate all the binding sites.
Okay.
Right? Okay, now gel filtration, what's the basis of separation there?
Density.
Size,
yeah.
right? Being able, whether or not you get in those beads or you don't get in those beads, right? Okay, so we want all of those molecules to hit that matrix at the same time,
Right.
so we can get good separation. If we put on too large of a volume, well, let me ask you, which ones go the fastest through this column? Big things, right? So you can imagine this portion of it has started to separate out, and the big things are down here, and the small things are up here. But by the time this stuff even hits the column, then those big ones are gonna be tangled up with these small ones, right? And you're gonna just have crummy, they're gonna be overlapping with one another, you're gonna get really bad resolution. So for gel filtration, a small volume is critical,
Okay.
right? The smallest volume possible.